My dear student, colleagues, and all the viewers who are watching this program live on Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar, and I'm happy to share with you all that today it's our 138th International Physics webinar. So good evening to all, and I think you are well and safe from Corona pandemic. So all we know that we are staying in a Corona pandemic situation, and recently the situation become worse. So we have to stay at the home for our safety. So it's very difficult for us to continue our academic program inside the campus. We have to start online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar, and we have successfully completed our 137th international physics webinar, including 2 Nobel laureate speakers. So today I'd like to welcome you all through a joint session between the Department of Physics, Pabna University of Science and Technology, and Department of Physical Science, Indian Institute of Science, Education and Research, IISER, Mohali, India, in physics. And we have with us here today Dr. Sudeshna Sinha, madam. And she has already connected with us. So I'd like to welcome our speaker. Madam, good evening and welcome to our International Physics webinar. And thanks for accepting our invitation, madam.
You're welcome.
So I think you have already come to know the title of this today's International Physics webinar, and the title is The Exploiting Chaotic Dynamics. And our speaker is Dr. Sudeshna Sinha, FASc, FNA, FTWAS, JC Bose National Fellow, Deputy Director and Professor, Department of Physical Science, Indian Institute of Science, Education and Research, IISER, Mohali, India. And you can see her educational and employment records. She has completed her MSc 5-year integrated program in chemistry, IIT Kanpur, 1985, and PhD from TIFR Mumbai in 1990. She has started her career as a reader at Indian Institute of Astrophysics, Bangalore, and she stayed there 1994 to 1996, and then she joined as a fellow, doctoral fellow at the Institute of Mathematical Science, Chennai, and then as a reader at the Institute of Mathematical Science, and the professor, the Institute of Mathematical Science, and professor, Institute of Mathematical Science from 2009 to 2011, and now currently she is working as a professor at the IISER, Mohali, since 2010. So we can see her research interest, nonlinear dynamics, chaos and complex system, complex network, and she got some awards. You can see the award, the elected fellow, the World Academy of Sciences, JC Bose National Fellowship, elected fellow, the Indian National Science Academy, New Delhi, India, elected fellow, the Indian Academy of Science, Bangalore, BM Birla Prize for Physics, 1998, associate member, International Center for Theoretical Physics, ICTP, Trieste, Italy, 1995 to 2000. So we can see her Google Scholar ID, and her citation is 4,125, and ResearchGate ID, and her research point is 39.95. This is her publication. So thanks for all of your patience. Now it's time to go to our speaker. So madam, thanks again for joining with us, and thanks again for accepting our invitation. It's your time, madam. You can start.
Okay. So let me, should I then go on presentation mode?
You can,
sorry. I made a mistake. 1 second.
Okay.
Where was it? Sorry. Where has it gone? I thought it was up.
It's minimized, so I think you can.
I know. 1 second.
So you can minimize this space. This space you can minimize, and then I think you can find.
Sorry. I'm. This is. Oops. 1 minute. Where is it? Can it be seen still? 1 minute.
Yeah, we can see now.
Is that okay?
Yeah. Okay, madam.
Okay. So let me start. So thank you for the. So thank you first for this. For the generous introduction. So anyway, as I was telling Dr. Dash, one day I hope I will have a chance to visit your department in person. But for now, at least, I have this opportunity to interact with you virtually. Okay, so what I thought I would share with you today is one particular thread in my research interests, I thought I would choose this thread because it brings together some very abstract and theoretical ideas with some applications. So it involves complex dynamical systems, and it also involves some directions towards understanding them. And then we would try to exploit our understanding of these complex systems to control them. And once we manage to control them, we can use the controlled system for applications. So this will be the thread. Okay. So, I'm a theoretician. And so for me, it is just fun when something which you have, only done in a very abstract way finds its way into real life use. So I thought I would share that with you. Okay. But I am aware that the audience here is not comprised of specialists in nonlinear dynamics, and so I think it is it's only reasonable to start with a very brief, like a crash introduction to the concept of chaos. After all, that is one of the main words in the title. So I will give some 10-15 minutes to it. And so my apologies to everyone in the virtual audience who know the concept very well, but let me run through it. Okay. So basically, we are dealing with classical phenomena. And to bend one of the well-known quotes of Eugene Wigner, the thing which I would like to first put up front is the unreasonable effectiveness of classical mechanics. So even to this date, though it's an extremely old field, okay, it has stood the test of time. It is still relevant. It is still useful. Okay. So what it gives us is this mathematically rigorous toolkit. It is so mathematically rigorous. There is, in fact, a branch of mathematics called dynamical systems, which has been feeding us important theorems from time to time. And it is also has enormous applications in engineering. So people who do nano-mechanical oscillators, maybe, for instance, still use essentially classical mechanics. And people who do astrophysics and astrophysical objects, which is an absolutely different scale, they too use classical mechanics. So it's almost mind-boggling the number of scales it goes across in relevance, both in time and in space. Now, what is chaos? So chaos, you can think of, is a concept which represents a new frontier in classical mechanics. So, if classical mechanics is, a polite way of saying a very old field, so this is like a new kid in the old block. And though it is new, it has given us actually a fundamental way to reassess the physical world, the classical physical world, okay, which you might have thought you understood very well, but there were all kinds of things which were not adding up, and chaos theory came in to propose a new way of addressing this problem. So what was the surprise? Why was it even necessary to think of a new science? So one of the surprises is that a large range of seemingly simple natural processes, something which you might have thought you understood very, very easily, they exhibited enormously complex behavior. And in fact, the complexity was often so high that it appeared as if it was evolving under random forces rather than simple deterministic laws. Okay, so basically, some completely deterministic systems displayed exponential sensitivity to initial conditions. And in practice, what would that tell us? It tells us that it's essentially unpredictable. Because if you have to know your initial conditions with exponential amount of accuracy, and if you lose information of the system exponentially fast, in essence, you really can't predict the system. So this is the delicious contradiction. There's determinism on one side, and there's unpredictability on the other side. You wouldn't have thought you would use both in the same sentence. You won't use the word deterministic system is unpredictable, but that is exactly what was observed. So this necessitated a paradigm shift. to understand classical systems. So I have not, in fact, put any noise in it. I've not put any quantum effects, just a nice, neat classical system. Even that necessitated this paradigm shift. And what emerged was this new science, which we called chaos theory. Now, one of the things which I find interesting from the sociological point of view is that this word chaos actually occurs in common usage. Okay. So it's a common English language. In fact, in India, we use it all the time to describe everything from politics to traffic. We say, chaotic politics, chaos and traffic, all the time. And, I'm sure there is a Bengali word for it, which all of you would also know. And, but this word was inducted into scientific terminology. And that is the interesting thing. So a common usage word became a scientific word. So, in fact, I have asked some of my friends in Europe, and they tell me that in even as old as Greek cosmology, this word had a place. So it referred to as an abyss, or something which precedes order. So it comes before order. It's the primeval emptiness of the universe before things came into being. So that was the system which was called chaos in Greek mythology. I asked my Chinese friends, and they told me that there's even a symbol for the word chaos. And in some sense, it had the same meaning actually as the Greek one, pre-order. Okay. And then to come to more modern usage, I mean, if you look at Webster's dictionary, to see the English meaning, you would find maybe synonyms like confused, disorganized, unorganized, disorderly. Such words will come up. And so that gives you a sort of, understanding of what you might expect of the phenomena that we are going to address. The first time it appeared as a technical term in scientific literature was around 1975 in an American Mathematical Monthly paper by Lee and York, very well-known mathematicians or mathematical physicists. And the paper said period 3 implies chaos. And the word chaos came in as a technical term in the title. So what is the key idea? The key idea is this. The present at any point in time determines the future, but the approximate present does not approximately determine the future. So in a sense, if you want to go back to the old question, does God play dice? It appears that God is playing dice even in a classical system. Okay. So the irregular motion of a deterministic dynamical system is so sensitive to initial conditions, as I mentioned just before, that it is impossible to predict in the long term. And to put it a little more technically, it is impossible to predict unless you have an infinite and perfect representation of analog values. So that is just to say that unless I can either in the computer as in numerics or in the lab where you actually have to, observe things or record values. So unless you can do it with infinite precision, which of course you can't predict effectively. And though, as I said, 1975 is probably the first time the word came in, even luminaries like Maxwell and Hadamard and Poincaré and Lorentz, this is not of the transformation, but Edward Lorentz, who was an atmospheric physicist in MIT, all of them recognized this problem and were uneasy with it and wanted to find a framework in which to understand it. And now, of course, the concept of chaos, which sometimes is popularly called butterfly effect, because it comes from this whole thing that, a smallest change, for instance, a butterfly flapping its wings somewhere, can cause a huge effect, like maybe a tornado somewhere else. So it's just a more dramatic way of giving a picture underlying the more dry statement that the system is extremely sensitive to initial states. And it's there also in popular imagination. I think there is this bestseller book, which some people, especially young people, like to read because it's very easy and may not be completely rigorous, but it's an interesting read, and became quite a big bestseller. And there are even Hollywood movies. And so once it becomes a Hollywood movie, you know how far it has gone into the psyche of the general popular imagination. Okay. So I will state the first simple, slightly imprecise characterization of chaos one more time. It is, in a sentence, sustained, disorderly looking, aperiodic long-term evolution. Owing to great sensitivity of small changes in the condition, it appears to be so unpredictable as to essentially look random. And the more precise signature of chaos is this particular exponent, which you have to calculate, which is defined in terms of small deviations in the trajectory and how that small deviation grows in time. So it's the ratio of the small deviation x naught at time t equal to 0, where you started, and how that deviation grows. And this is the exponential growth of it. This reflects that exponent, because, you know, if I pull the t here and put a e to the power lambda t, this ratio is e to the power lambda t. Now, this is a very difficult exponent to estimate because it involves two limits, t tending to infinity. It's a long-term question. And of course, it also has this thing that the initial difference in the states should tend to 0. Okay. But I thought, instead of giving a mathematical definition, it's always more fun to give a very simple example. Because you see, suppose I told you a very complicated system gave a very complicated, dynamics. Then you would say, but what's the surprise in that? You've made something very complicated, so something very complicated came out. But I'm saying the opposite. I'm saying I take something very simple, very, very simple, but something very, very complicated comes out of it. So you can't ignore the complicated thing by saying, oh, it was complicated, so I don't have to look at it. So here are a few examples. The first one is a discrete time system. Okay, so these are maps. So these are maps. So which means that the time, so n is discrete time. It's an integer. Okay, and the state of the system at time n plus 1. So you can think of it like a stroboscope. You measure the time, its state at time n, and put it in a function, and to get the state of the system at time n plus 1. Simple. You can do it on a pocket calculator. I mean, if you wrote a program, it would take 10 seconds to give you, say, 10,000 steps. It's a very simple thing. And even analytically, you can see how simple it is. So here is R. R is just a number. It could be, say, any number between 0 and 4 in this particular case. It's some real number. So it's a parameter. And so the dependence on x is just xn and xn minus xn square. So the nonlinearity is just quadratic. Simple quadratic system. The second thing, absolutely in the same class, is not even a quadratic nonlinearity. It's a piecewise linear system. So if I plotted this thing, 2xn mod 1, I would get two straight lines like that. And the third example, called a tent map, because it looks like a tent, is a map like this, which means that essentially it consists of two linear paths. So these are the simplest nonlinear systems you can think of, because this function, xn plus 1, is given by a function which is nonlinear, but simple nonlinearities. Now, the action of the map is twofold. One thing, stretches. So which means that two neighboring things, so if I was there at x and x plus delta x, they would actually move exponentially fast apart. So it's a stretching action. But if they just stretched and ran off to infinity on both ends, again, what's the fun in that? It's a bit boring. The interesting thing is that there is a fold operation. So that is where these maps are actually what are called non-invertible. So they have non-unique inverses. So basically the fold operation says that the iterates come back to the same region. So think of the complexity. They are running away exponentially fast, but are forced to come back to the same thing. And as a result, this is what you got. So n is this number here, the iterate number. Xn is the state. if I looked at this, this looks completely random. I could have taken a random number generator from my laptop and, put them together, and it would have looked pretty much like this. However, this one was generated from, actually, I think this particular map. Oops, sorry. It would have been absolutely the same for any of them, more or less indistinguishable. But the thing is that such a simple deterministic equation, going almost like clockwork in the background, is generating this bafflingly complicated time series. If you did not have any idea that it came from this very simple equation, you might have thought it was just a random number generator. And here is a 2D one. This is more, one can demonstrate the stretching and folding even more dramatically. So this is a invertible area preserving 2D map. So here again, see how simple it is. Xn plus 1 is just 2xn plus yn mod 1. And so mod 1 is the fold. It keeps everything in the square 0, 1, 0, 1. And yn plus 1 is just xn plus yn. Very simple. Okay. And this is a picture of what this mapping does. So to demonstrate it, they took a picture of a cat, and each pixel, so if I took a little black dot here, it would be mapped. So suppose the dot was in some place in your XY coordinate. It was mapped by this formula to another one. And this is the action. This is just one iterate of the map. So the poor cat first gets stretched. Then, because of the mod 1 operation, it has to be cut and folded back into the square. And this is the resulting square. One iterate, the cat looks like this. So the information has been scrambled to such an extent by just one iterate of such a simple looking map that is almost unrecognizable. So the poor cat is completely mangled up. So it's not just that quantum mechanics has cats, chaos also has some cats. We do bad things to them, but it's there. Okay. So now what I thought I would, discuss with you is, can we use this new knowledge of classical dynamics, the stuff which we are beginning to understand, to do something for us? There's so much knowledge. Is there some way of using it? So before one uses anything, so there appears to be lots of richness there, lots of patterns, lots of things happening. But in order to use something, as they say, to harness all the richness in the dynamics, one has to be able to control it. So what I will try to show you quickly in these two approaches is that the first approach will be to control the chaos. And this approach is going to give you strategies to extract a very large range of patterns from the nonlinear dynamics. Okay, the first paper in this direction was in this particular PRL. And the second thing, if I have a bit of time, here I might go a bit quickly, is to exploit not just the nonlinearity, but noise. So one thinks that noise is one of those things you want to suppress, you wish it wasn't there. But I will try to show you that maybe noise and nonlinearity can interplay to give you something productive or to give you some constructive thing. So this is a more recent PRL, and there are many to follow. So let me get on with the first one. So here is a very, very powerful control scheme. And the scheme is very simple. So once I state it, you wonder how it works so well. So it is called thresholding. So what it says is this. So X variable is going around. Okay. But we let it do its own thing. But if the X exceeds some prescribed threshold level, X star, then I just reset it to X star. So basically, it's like a Lakshman Rekha. If it goes out, I grab it and pull it back. That's all I'm doing. But when it's under the threshold, I let it go. I have no problems. But beyond a threshold, I say, I have to bring you back. And the broad principle here is called dynamic range limiter. So basically, it has had a normal dynamic range. You limited it a little bit and pulled it back. That's all. But the action of this is extremely potent. So there was this very complicated chaos, which looked like, as if it was doing all this random thing. You just put in this thresholding, it clips that complicated chaotic dynamics to exact cycles. So you can get stable desired patterns from this chaotic temporal sequences by just this small intervention. And why is chaos advantageous? Why would you even want to do it? Suppose I say I gave you a periodic system and, why don't you do it with that? Why should I bother with chaos? The thing is that chaos is advantageous because it has a large range of patterns. And so it can take these patterns and it can clip them to many different behavior. So from the same system, you can make it behave in different avatars by just putting different levels of thresholding. Okay, so this was an old idea of mine, which was from 93, but found more use later on. So, for instance, if I took that same chaotic logistic map, which was, say, xn plus 1 is, let me put a value of r for xn 1 minus xn, that one. And all I'm doing is I'm saying if xn is more than x star, I reset it. That's all. And then if I do that, if x star is anything less than half, I get fixed points. So it'll always stay at 1 point forever. If it's between some range, it's a period 2 cycle. So it'll be x1, x2, x1, x2. It'll just bounce back and forth. In another range, it'll be period 4, cycle between 4 values. Period 6, 7, actually, literally every period. So threshold control gives a lookup table. So on one side, you have the threshold. On the other side, you have the controlled orbit. This engineers really like because you've given them a table and they can just extract things from it. So here is an experimental verification. So that one you can do in theory exactly by doing some little bit of symbolic dynamics. There's some technique to it, which I don't want to bother you with, but you can also verify it. So this was done with my experimental colleague, Murali in Chennai. And so these are oscilloscope traces. So this is a chaotic trace. There are actually lots and lots of dots. It's literally all over. And I put some threshold. I think I put it at 0.8 and I got exactly 6 cycles. So this is going to repeat exactly after 6 steps. So 1, 2, 3, 4, 5, 6 repeated. 1, 2, 3, 4, 5, 6 repeated. And the thing is that these cycles actually can be shown analytically to be super stable, which means even the smallest, even the fairly large perturbations pulls it back to the cycle in very short time. So in engineering terms, it has very short transients and latency. So these are things you want to minimize, and that's inbuilt. The other thing is a bit of a technical point, is that chaotic systems often have this ergodic property. That is, the trajectory explores a certain space. It's very democratic. It visits every part of that space. And this property actually helps us because it guarantees that sometime or the other, it's going to exceed that threshold because it's, doing a chakkar over the whole space. And so it is guaranteed that when it does that, it will be pulled back. So it has to be controlled. And it is, in fact, controlled very easily. So as I went to repeat the other point, because the same system can give such a wide range of stable patterns, you can use the chaotic system as a flexible pattern generator. So I can make it be whatever I want it to be. I can make it a 1 cycle, 2 cycle, 3 cycle, 4, whatever, depending on what my need is. And I can do it very flexibly. So here is another set of oscilloscope patterns, which gives 2, 4, I think 7 and 10 cycles. And what is nice for a theorist is that all of these experiments came well after the theory. So essentially, I'd done the full calculation of the threshold and control period correspondence. And after that, my experimental colleague essentially took the system and put those thresholds and got what was predicted. And later on, many people have done much more. And since I know Dr. Dash himself has been in Japan, so I should mention this group of Morai. They have done an excellent bit of work. They have done integrated circuit implementation of these threshold-coupled systems. They have done, I think, 150 in one chip. So they have taken this idea. So Murali had done it on a circuit which was on a table, which was, not too small. But Morai's group have actually implemented it in a very, very nifty way. So it works. Now I'm going to run through very quickly over a bunch of slides. You don't have to think too much. These are all given by, these are all chaotic systems under thresholding. So I had talked about maps. Those are discrete time systems. But of course, all of you understand ordinary differential equations more intuitively. So for instance, here is a nonlinear third order differential equation, which given these parameters appropriately has chaos. And this is the chaotic attractor, which you see on the oscilloscope. So it is, essentially not aperiodic and, quite very complex looking. And as we put different thresholds, it gives these neat periodic orbits of different orders. You can also do it for the double scroll Chua circuit. So this is slightly more complicated because there are two sides to this chaotic attractor. Here also, if you put different thresholds, I can get this whole chaotic attractor to be a fixed point. So then on the oscilloscope, I just always see a fixed point and nothing more. Or I can change my threshold to make it give periodic orbits of different periodicities. As you can see, this period 2, this period 4, it has looped around 4 times. It also works for hyperchaotic systems. These are systems which have more than one positive Lyapunov exponent. So that's another way of saying, a little bit loosely, that it has more than one unstable direction in which it is unstable. So which means, so when we first did it, we thought that we are controlling one variable. So we are saying, so suppose there are 4 variables, so x1, x2, x3, x4. But we are just taking, say, x1 and doing thresholding on it. Is that enough? Because, the system is flying apart in more than one direction. Is it enough to just threshold one? Will it work? And the answer was it did. So here is this hyperchaotic attractor, which Murali also did as a circuit experiment. So it works in the experiments as well. And here is one particular controlled orbit. There is literally like a library of controlled orbits, very pretty ones, which is there listed in this paper. Now, I thought I'll spend 5-10 minutes, maybe, trying to just give you an indication of another idea. So this idea is to say that, okay, you have chaos. You seem to be able to use the rich variety of behaviors to get this versatile pattern generator. Can I exploit this to implement something which all of us are after, namely to do computations? So can I make this chaotic element into a logic gate? And of course, if I just made it one logic gate, it's fine. It's proof of principle. But I want to do a little better. I want to make it a flexible logic gate. So I want the logic gate to be able to switch between behavior. So maybe from NAND, NOR, AND, OR, XOR, whatever, by just changing a simple parameter. Is this possible? So chaos for computation now. So the hardware are these threshold activated chaotic elements. So chaotic element plus the threshold control. We think of it as a chaotic chip or the chaotic processor. And the programming aspect of it is to fix the threshold, is to say that is the work we have to do in the engineering aspect. What threshold should I fix so that my chaotic system does what I want it to do? So I want it to give some desired operation. And so what set of thresholds helps me get it? And so these are the basic papers. And there is a very nice article written about this work in Scientific American, not by us, but obviously someone else reported on it. But I think this Scientific American paper is nice for first read. So aim, implement all basic logic gates flexibly using a chaotic element. And the hope is that it'll have the ability to switch between different logic roles or different operational roles. If we could do it, it would give us a dynamic architecture. So I could then make these the ingredients of a general purpose device. which would be more flexible than statically wired hardware. So just making hardware out of families of NANDs or NOR. Instead, I would have a way of changing my logic gates as needed. Now, here is an illustrative example. Okay, there are many complicated ones, but I thought I'll just give you one. Back to chaotic map, because I can write it so easily. So how could this chaotic map behave as a logic gate? So say the inputs is just X, add to it, whatever its initial state, I1 and I2. These are my two inputs for a two input logic gate. What is the output? If after threshold mechanism, it becomes more than threshold, I say output 1. If it's less than threshold, I say output 0. Simple. Just a threshold activated output. Now here are the truth tables of the basic logic operations, say I want to implement. Okay. If it's one input, then I just put I here instead of I1 and I2. Now, in order for the same chaotic system to serve as any of those gates by just changing the threshold, the necessary and sufficient conditions that need to be satisfied simultaneously are these set of equations. So I have to be able to find solutions for all these equations. The question is, are they even there? Can we even get these solutions? What kind of functions give it? Okay. And the answer is the interesting part. Robust solutions exist when the system is sufficiently nonlinear. So that is the advantage of nonlinearity. That is, in fact, chaos is very nonlinear, so it gives this advantage that you cannot even get all these gates to happen unless you have enough nonlinearity. And so in some sense, the nonlinear dynamics has this richness because of which, it is possible to have those solutions. And the other good part, in case we forget, is that it's also still deterministic. So which means I can design. So I can say that, okay, I've done my calculation beforehand. I'm giving you the threshold. If you do this, you'll get this. Okay. So the richness of the dynamics allows you to select all the different requisite responses from the same module. And okay, so these are, some of it was also presented to the engineering community in the IEEE papers. And there are a bunch of patents which is used to develop this commercially. And so here is one of those. This is not a map. This is actually a ordinary differential equation, but I thought it's a nice picture. So here are the inputs, stream I1, I2, and this is a voltage here. And we have given it the signal, the threshold, to behave as NOR and NAND. And this is how the system responds. It morphs easily between the NOR responses and the NAND responses, exactly as we want it. So it's a morphing, reconfigurable logic gate. And in fact, you can get any logic operation by just varying the number of iterates. So you can say, first iterate will give you these, second iterate, I have even more possibilities, etc. So here's a very pretty colored picture which tells you all the different logic responses you can get by tapping the system's temporal state at different iterates. So this is the n of your xn. So at n equal to 1, I could be this if I took this x naught. At n equal to 2, I could be all these gates, etc. Obviously, the stuff here is not practical because they're too sensitive. However, the first 4 are very, very easily implementable. So 4, 5 iterates is perfectly okay. After that, you lose because your sensitivity gets better of you, and so you shouldn't push it too much. And this is the company which is developing the VLSI implementation of this chaos computing. And they have some demo circuit chips already, which are reasonably small, have reasonably low power. And there are some write-ups on this in various magazines, and also from MIT Technology Review in 2006, because it has some technological implications. Though, as I said, I'm actually a theorist. So that's the fun part for me, because all of it was, doing some analysis, and the spin-offs were not what I was working towards, but they just happened. Okay. The last, I think maybe I have around maybe 15 minutes or so, maybe 20 maximum. So let me just use it to indicate another idea. So now I'm trying to get together noise and nonlinearity. Now, this happened for an obvious reason. While I was giving talks on this in many different places, some people started asking me, but you'll always have noise, and things might, you might have problems. So, of course, we had done sensitivity tests, etc. But then I thought, let me change the question. Let me ask a different question. Can noise help us? So, of course, this issue has received enormous attention, because as devices and platforms are shrinking, we have to deal with fundamental noise. It cannot be suppressed, cannot be eliminated. We will encounter it. So people are thinking about it. There is some previous work which inspired us, and that was on stochastic resonance. So this was essentially, if I have to give a one-line summary of it, cooperative behavior between noise and dynamics. And this interplay often gave these counterintuitive physical phenomena. So, for instance, in stochastic resonance, it was shown that if you can add an appropriate amount of noise, it can boost the signal. So, usually noise is supposed to be the enemy of signal, right? It's the one which suppresses it, degrades it. But in stochastic resonance, the appropriate amount of noise, there's an optimal medium amount of noise, which facilitates its detection. And in fact, engineers knew this because they call it dither. I mean, they used to put it actually, even they still do. So the signal to noise ratio is maximized in the presence of non-zero noise. Okay, and people have been using this effect in many other things, not just in applications, but trying to understand biological systems, or geologists, ice ages, etc. So it's just a concept which has grabbed the imagination. What are we trying? We're still going back to logic. So what we are searching for is reliable logic circuits which can exploit nonlinearity in the presence of a noise floor. So given some noise, does it work better? And so this, we hope, would play a role in the design and development of devices, because of course both noise and nonlinearity is probably going to be crucial. So what we show in a nutshell, the basic result up front, is that the response of a nonlinear system, which has different stable states, or multi-stable system, to a stream of input signals, was shown to consistently be a logical combination of the input signals only in an optimal band of noise. So if we gave no noise, it did not manage to respond like a logic gate. If we gave it too much noise, it's of course terrible. But in the middle band, it did perfectly. So here, let me give one example. There are many examples. I'll give the simplest one. Here is a nonlinear system. Very simple, not chaotic, just simple two-well system. X dot is some f of x. I is my input signal, which I'm giving low amplitude. Okay, because you don't want to hit it with a big amplitude. In all applications, amplitude has to be low. And it has some additive noise here. You could do it with all kinds of noise. People have done it. But let me just do this. Now, f of x could be anything. It just, only thing we want it right now is that it has distinct wells. So say, for instance, a bistable system. Okay. And then you have two logic outputs. Again, two input, I1 plus I2. And because I1 and I2 are independent, it gives three-level aperiodic waveform is hit. Okay, because it's what the world gives you. Whatever I1 and I2 I want to give you, I give the system. So here is, say, one particular example, extremely simple. This f of x, which gives me these two wells. Okay, one is roughly around -1, one is roughly around +1. I think of it as an upper well and a lower well. And this is a schematic. So these input bits is my input stream given to me by the world, by the user. This is the noise, which is there. You have to live with it. This is my nonlinear system, which could be that bistable system or any other bistable system or even multi-stable system. And what we get out of it is this. So the bistable system will hop from well to well in a way that is consistent with the logic output. So the output of the system, you can say, is 1, say if it's in one well, 0 if it's in the other well. Okay, maybe upper well is 1, lower well is 0. And it is going to go from 1 to 0 in an appropriate way depending on the combination of I1 plus I2, according to the truth tables of logic. Okay. And this one picture is a summary of what I was trying to say. There are many, many things, but this one I hope you can carry back with you. In this system, here noise is low, noise is medium, and noise is high. When noise is low, even to the eye, you can see that, okay, this set here is the input stream. Okay, so it's some aperiodic 3-level system. Okay, 1, 2, 3 comes in any old order because whatever is given to you, random order. Now, what is the system doing with respect to this random input? Here you can see that sometimes it gets stuck on top. It's not responding to it. It should have been down here at the same level, okay, but it doesn't hop back. So low noise is inconsistent. It is not giving you consistent response. Let me hop to the high noise. High noise is very bad because this, nobody is going to get an output out of it. It's hopping back and forth. It's very fuzzy. So this is no good. I can cut it out. But the middle noise, this is perfect. It is hopping consistently and it's staying in the well as we want it to. So that is the whole thing. So in summary, for very small or very large noise, system does not give consistent logic. But in this wide band of moderate noise, it produces the logic outputs consistently. We've done it for like a million million inputs stream and checked it and found out the probability is absolutely close to 1. And of course, like everything else, this was verified in proof of principle experiments done by Murali and his student Raja Muhammad, along with the rest of us in this particular paper. Okay, so that is the crucial observation. Logic output is robust and consistent only in the optimal band of noise. Okay, you can also add a little bias. This is just a constant voltage, so nothing more. And this changes the symmetry of the wells. And now it allows you, in addition to noise helping you, this bias helps you morph between logic functions. So I want to take the idea of the first part, add noise and get something which is reconfigurable and also good with noise. Okay, and so here is the probability done. This is a very intensive calculation. It was done over, as I said, a million sets of inputs given randomly to the system. And here is that constant bias. Here is noise. You see this bright spot here is 1. That's where you want to be. It's a sweet spot of operation where everything works perfectly. And you can see that it comes in a medium noise. Okay, this is low noise, this is high noise. Here too, it comes in the same band. But as you choose a different C, this gives you NAND and this gives you NOR. So you can switch functionality also. And that's the fun part. Okay. Some more experiments followed in very different systems. This was a nano-mechanical oscillator operating in the nonlinear regime where 2 different vibrational states coexist. Okay, and it was done in the lab of Mohali in Boston, and they had fabricated it from a single crystal silicon using e-beam lithography as usual. And these are the results. So here is again the same thing. This was for AND, NAND. This is for OR, NOR. Lots of noise, no good. Less noise, inconsistent because it gets stuck in the well and can't respond. Middle portion, moderate optimal thing. It is quite perfect. One can do it for different kinds of f of x, right? I did it for a very simple thing, but I can choose some interesting bistable systems. So with this group in Japan, Ando was a student at that point. Kazu is my old-time collaborator. We tried a biological system. It's the same principle, but it was a function which represented a synthetic genetic network. And here too, we managed to get these flexible logic operations optimized in a nice region of noise in the middle. Okay. My collaborator Ed Helen in North Carolina, he later on did an electronic analog of this synthetic genetic network. This was actually a little bit hard to do. He had to put a student in who ended up, doing it over 6 months to a year almost. But at the end, it worked. And here is low noise. As you can see, it's got stuck here, the response, or stuck here. No good. It's not hopping. It has to hop. It has to toggle its output 0, 1, something it has to do. It's not doing it. But moderate noise, it manages to hop exactly as you wanted it to. So just thought I'll show you a few different things where, the idea has been seen to work in rather different systems. Okay, and there are a couple of very nice articles written on this, on these things in Physical Review Focus and in Science News. These are popular articles and explain it better in easier words than I am doing here today. Okay. I thought I should have one slide to tell you that lots of people from other groups are also working on it. For instance, a lot of work in China, I find. I don't know them, but I see their papers. They have tried colored noise, they have tried time delays, they have tried other information-based measures, like bit error rates, all kinds of things. They have tried from bistable to tristate systems, etc. Lots of people are also doing it in different experimental systems like VEXELs or other resonators. I saw something on thin films. I didn't quite understand it, to be honest, because I'm not an experimentalist, but I see that they have implemented that same protocol. So seems to work. And, some of it I understand, some of it I don't, but it seems to be based on that basic idea of logical stochastic resonance or getting optimized logic operations in a window of noise. Okay, so this is my last 2 slides. I will end in 5 minutes. So I just thought before I end, I'll show you 3 slides. You can see it, without too much depth. So in the beginning, I was talking about chaos. Then I went into non-linearity, but I did not have chaos there actually. I had bistable systems. Can one take the idea of chaos and the idea of bistability and see if you can do something together? And the answer is yes. The thing is, chaotic attractors can also be bistable. So what do I mean by that? Certain nonlinear systems have dynamical attractors, which could be complicated chaotic attractors, but they occupy different regions of phase space. Okay, so they sit in different paths. And so in some sense, they can hop from attractor to attractor. So when you think of your standard bistable thing, you're hopping from fixed point to fixed point. Fixed state, steady state at the bottom of this well, steady state at the bottom of the well. Now you just free your mind. There's a chaotic attractor in one part and a chaotic attractor in the other part, and they can also hop. So you want to have this idea of hopping between attractors, but now there are more complicated attractors. They are chaotic attractors. So you're combining this chaos computing with the logical stochastic resonance. So basically, here is this complicated chaotic attractor. Here is another one. And as you give these inputs, the trajectory jumps from here to here. So I can designate this to be output 1, this to be output 0. And according to its input, if the jump is consistent with logic, I can say that the whole system is now a complicated logic gate. Okay. And why is this interesting? Here we found that the input signal could be exceedingly small, like 10 to the power minus 3. So the chaotic attractor, say, is of order 1, but the input is really, really small. So when it is so sensitive to inputs, people like it. It means it takes less power. You give it an extremely low amplitude signal and it responds. Response is huge. Okay. So a small change gives a significantly different dynamical outcome. So it hops in response to a very small thing. And some people, including us, have called this tipping point, because you push the attractor and you give a little push and it jumps to the other attractor. Okay, so you can think of it as a tipping point. And in another thing, you can think of it as a generalized stochastic resonance, because it is using complex attractors now, not just periodic cycles or fixed points. Okay, here is a electronic circuit analog of it, just to say that it works. This kind of jumping between attractors in response to inputs actually can be done very consistently and pretty easily, actually. Okay, so in summary, the noise flow can aid the reliability of the logic operations, just as I had told you before, except that now the switching is between states which are more complex. So it's a generalized logical stochastic resonance. And remarkably, the amplitude of the logic input was very low. And we don't understand this, but we pushed it even smaller than the noise strength. I really don't understand this part, but it worked, even in the experiments. So for instance, it was like if the input signal was 10 millivolts, which was actually about 100 times smaller than the noise which we were giving, just to test it, for fun, which was about 1 volt. So I don't know how that worked, but clearly it works with extremely small input signal. And so low amplitude gives highly amplified outputs. Okay, that is the takeaway message of this. Last slide. So what I hope I kind of wanted to convey to you is that nonlinear systems, which are actually abundant in nature, it's hard to actually find linear systems. Most of them are approximations of a nonlinear system, where you say, okay, the nonlinear terms are small. So nonlinear systems are literally abundant and widespread. They can also be readily engineered and made in the lab. Quite easy. So our central idea was to exploit chaos for something, and that something was to make a computing device, okay, a reconfigurable logic gate, as it was. So rather than suppress chaos, we tried to use the opportunities which chaos gave, namely all those temporal patterns embedded in it and the determinism which allowed us to control it into these responses. So we could design the responses. That was the idea. And lastly, I also indicated some directions to use the noise in conjunction with nonlinearity to get more reliable logic operations. Okay, so these were the things I've hoped to convey to you, and that brings me to the end of my talk and my time as well. Yeah, so should I maybe so I had so these are things which people can look up. I'll leave this slide and maybe should I get back
thanks, madam, for your wonderful presentation. So if you allow, we can start discussion session.
Sure.
We have got some question.
Yes.
So yeah, okay, I can add those question in the screen, so I think you can also see. So can this chaotic logic gates be applicable to computer architecture software, or can one day we can get chaotically controlled computer?
Right,
and
right.
how
Yes.
this chaos can change computer technology?
Right. So that is, of course, the hope. So this company Chaologics has been making have the first generation of chips. So the idea is, of course, that I don't think, I will be frank, I don't think it's a replacement, but I do think it makes a very good module which can, so for instance, Chaologics has sold some of its technology based on this, exactly what I've been telling you, to ARM to put it in mobile devices, for instance. So what happens is you can use the flexibility either maybe as a field programmable gate arrays, or maybe like an ASIC, like, I want a very special application in mind, then I make the most optimized set of logic gates to get that. But then I will need less space, because I won't have to cascade gates to get it. So I could implement it in that way. So it could go in as modules. So the only thing which has been a little bit of a thing is that of course it's based on standard technology. That part is not hard, but uh, you know uh, the market, it has to be competitive. It's actually very competitive in terms of size and power, but it's not so competitive in terms of the processes which are needed in the factory to make it. So that's what I believe it is. So now it has gone into the business mode, which I am out of. I mean, I just gave the idea, and of course it's based on my patent, but so attempts are on, and it has had a little. I think it'll take years. But yeah, the hope is it is actually much more easy to implement than some other technologies. That is for sure. Yeah. I don't know if I managed to.
Yeah, thank you, madam. We have another question. So how the idea of the chaos is related to idea of chimera?
Okay, to chimera. Yes. So actually, I would say that chimera states and chaos are not. I mean, there are chimera states which are not chaotic. There are chaotic states which don't support chimeras. Now, first thing you have to do is that chimera states arise in spatially distributed systems. Okay, so basically, so most of what I was showing was one system. Okay, so one chaotic map, or one ordinary set of ordinary differential equations. A chimera state will come if you have a collection of them, a coupled system, say maybe 100 of them. Now, for instance, there are a lot of observations of chimera states in, say, if I took those chaotic logistic maps and I coupled 100 of them in certain parameter regimes, depending on the coupling strength and the nonlinearity, one observes these. So what is a chimera state? So chimera state is a state where there is symmetry breaking. So by that I mean that there are, in the same system, there are parts of it which are regular looking, interrupted with parts of it which are not. So for instance, even if you had a bunch of phase oscillators doing nothing much, some of the oscillators would be synced approximately, and then there would be parts, some bunches of them will be not in sync. So it is a sort of mix and match of two very incongruous things, like the same system. So they need not be chaotic, but a lot of chaotic systems show it. Of course, in none of this I have used chimera states, because chimera states are actually hard to control. See, I mean, when you sell an idea to an experimentalist or to an engineer, they like the system, the idea to work like with all the time and with least amount of work, as in least amount of intervention. So chimera states, I don't know the applications of it much. I don't think that is the angle in which people are working. Most people are trying to understand it. And so, as I said, there are definitely chaotic systems, coupled chaotic systems which show it. But there are also simpler systems which show it. Yeah.
Thank you, madam.
Yeah.
We have another question. So, can you explain very briefly how the idea of the chaos is brought in quantum system, and can we use this connection in quantum computing?
Yeah. The first question I can answer. The second question is open. Because okay, but the first question, let me try and answer. So as you can see that chaos, the rigorous notion of it, is completely classical. It's a classical system. Even in the definition of the Lyapunov exponent, you need trajectories, right? You say two trajectories, x going in time and another one. So just in the definition itself, you would have some difficulty thinking of the quantum analog. However, people, especially in the 80s and 90s, in fact, most of my thesis was quantum chaos, is because people were very excited to think of ways in which you can find out how a quantum system whose classical analog or semi-classical analog is chaotic, how does its quantum mechanical properties change? So by that, I'll re-say it. Suppose I take a system which is classically chaotic, I quantize it and I get a quantum system. I look at it, then just a quantum mechanical properties, say maybe eigenvalue spectra. Okay. So then I look at the same system which is simple, regular, and look at that spectra. Is there anything there which would indicate that its classical analog was so different? Or is quantum mechanics just forgets where its classical analog? It has no way of knowing the difference. So the answer was actually very interesting. There is a huge difference. So that was the quantum chaology, which Michael Berry calls it. And one of them was the distribution of the levels, eigenvalues. So for instance, random matrix theory played a huge role there. So level repulsion came to be associated with chaos, and level clustering came to be associated with regular spectra. So level clustering means that if you lined up your eigenvalues, there was a chance that the difference in the levels was going to be zero. So they would essentially, like you thought of a ladder, those rungs of the ladder could accidentally come close. Those were the classical analogs of those were regular. Whereas actually if the classical analog was chaotic, the statistics was GOE, or was of a random matrix given by Gaussian orthogonal ensemble. So that, and there were many other statistics from like delta 3, all those are very, very technical, but essentially from statistics. But so the idea was, take a system, see its quantum mechanics, and see what the difference is. So that was the effect of quantum chaos. But you can't actually take, you can try to go as much possible semi-classically. So Gutzwiller has a very nice trace formula where one side is density of states, completely quantum mechanical. The other side is a sum over periodic orbits, completely classical. And he has this famous formula, but that is pretty much the only one we have, which has a classical object on one side and a quantum mechanical. So it's a difficult system to because quantization actually depends on the existence of tori, which is a regular system. So even to quantize a classically chaotic system is it's not an easy notion. So in terms of quantum computing, some efforts are being made to relate quantum information to some of the properties, which relate again to level statistics and things like that. I think it's very open. Yeah.
So thank you, madam. We have another question. So can this chaos theory be applicable to photonics?
Since I'm not in photonics, I don't think I can give you a very honest answer, to be fair. All I know is that there are so my colleagues tell me who actually do some of these things, is that they feel that they can definitely put in some of these ideas into their devices. So there's a group in Mexico which has done some of it, but they are mostly optoelectronics, and they have got some nice implementations, which they of the same idea, but of the thresholding idea, that the first part idea that they did. So at the end, I don't have a collaborator with whom I have actively worked on it. If anyone has an idea, that would be wonderful. I mean, that's how collaborations go.
So this may be the last question, madam. So is chaos theory related to geometry or topology of nonlinear system?
Oh yeah, I mean, of course, yeah. So I didn't, of course, indicate any of those aspects, partly because it was, it would become like a course then. So for instance, of course, this whole thing of the strange attractor or the fractal geometry, or the fact that the dimensions are no longer integer, in many of these systems. So all of these are absolutely very, very closely related to concepts which are completely rigorous. That's why I said it's mathematically very rigorous, actually. So for instance, even so a lot of work is there in characterizing the geometry of the attractor, which is the set of points on which the system settles down to after the initial transients. And those have very interesting properties, like, as I said, one of them it has a fractal dimension which is non-integer and is somewhere, so it has a non-trivial property on this set of points there, so you can do those calculations pretty easily now. In fact, some of them are even made into little computer modules, because people do it so often. People also do it for time series, which they think have come from a chaotic system. They may not be able to tell which one, but they can analyze it through correlation dimensions and all, and find out the properties of the attractor. Yes, absolutely. I mean, there's a huge amount of work on it, and of course, in Hamiltonian systems, a lot is known on on the space on which the system lies for a regular object and for a chaotic system. Yeah, definitely.
Yeah, thank you, madam, for your wonderful presentation and nice discussion session, madam. So I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, madam, for accepting our invitation. So the main aim of our program actually is to motivate our students, and I think they have motivated by your presentation. So thanks again.
They're most welcome to email me if they want anything or any specific references. You're most welcome to write email to me. I tend to.
And after the COVID, actually, I think we can invite you for a face-to-face presentation.
That would be very nice. Yeah. I'm planning to visit some people in Dhaka also. Maybe time I'll come to you all also. Okay. Thank you very much for having me. This was a lot of fun.
It's a pleasure, man. Bye. Good night.